So now we are going to talk about some limit theorems. We have already seen that there are different types of convergences, namely convergence in probability, convergence almost surely, and convergence in distribution. Long back we know that convergence in distribution actually plays a major role in statistics, especially in estimation and testing. So when the sample size is large, then we might want to investigate what is the behavior of the statistic, which is nothing but a function of the sample observations. So today we are going to discuss some convergence in law, rather some theorems relating to this that is relating to convergence in distribution. Now to this end, one simple thing is what is known as the Lindbergh-Levy theorem, or Lindbergh-Levy, which is known as central limit theorem. So central limit theorem is nothing but some theorem or a particular type of theorems or results that deals with the convergence in distribution. So today we will discuss mainly two such theorems. One is Lindbergh-Levy theorem, another is Lyapunov's central limit theorem. So it is clear that these two theorems probably give us more or less same thing but under different conditions. So naturally in practice one may encounter different types of conditions depending on the sample or the population from which the sample is drawn, or maybe the form of the estimator, all sorts of things are there. So in this respect we need to study a few more central limit theorems, but today we will start with the first, or rather the basic central limit theorem, which is known as Lindbergh-Levy theorem. And then we will discuss Lyapunov theorem. Today we will discuss the proof of these two theorems. Central limit theorem actually commonly known as CLT. Basically it deals with convergence of a sequence of random variables, convergence in law or distribution. That means we know that there are several modes of convergences. So we will discuss through CLT how a convergence in distribution can hold, or what is the theorem. We will actually prove a couple of theorems based on this type of convergence. Another important thing that we should note immediately, that independent random variables, basically it indicates that sum of many independent random variables will be approximately normally distributed if each summand has high probability of being small. That means each summand, each component in the sum, it has a high probability of being small. Another type of CLT we can prove that can hold for dependent random variables, because basically by CLT we usually deal with independent random variables, but that is not everything. We can have other CLTs or central limit theorems that deals with dependent random variables also. So let us go back to a little bit of history, in the sense that this central limit theorem actually starts with de Moivre-Laplace limit theorem, which actually deals with the convergence in distribution of a sequence of Bernoulli variables. That means how one can show that as n goes to infinity, some function of the binomial random variable can go to a normal distribution, and it can be shown that the limiting form of the distribution is a Gaussian distribution or a normal distribution. Then comes Lindbergh-Levy theorem, which deals with the independent and identically distributed random variables, and then comes the Lindbergh-Feller theorems and Lyapunov's CLT and so on. But remember one thing, all these theorems, they actually deal with independent random variables. So the natural question would be whether there exists any other CLT that is true for some dependent variables. Fortunately the answer is yes, and there are some theorems that hold for martingales and Markov processes, which are nothing but some form of dependence among the random variables. But today, and maybe in the subsequent few subsequent talks, we will not really discussing this CLT for dependent random variables. We will stick to only the case of independent random variables. So let us state the simplest possible central limit theorem for independently and identically distributed random variables. This is known as Lindbergh-Levy theorem. It states that suppose xn is a sequence of independently and identically distributed random variables such that expectation of xk equals to 0. That means it has mean 0 and variance of xk equals to sigma square, which is less than infinity. That means it assumes the existence of moments up to second order. Then take sum of xk's like x1 plus x2 plus xn and let us denote this by Sn. So we will investigate the behavior of this function Sn as n goes to infinity, in the sense that what would be the distribution or whether the distribution of Sn converges to a random variable which has a particular form of distribution as the number of variables or the sample size in statistics goes to infinity. In fact, it can be shown that as n goes to infinity, Sn by sigma by root n goes to tau, Sn by root n sigma goes to tau in distribution as tau goes to where tau is a standard normal variable. Now let us consider, now we know that there is a one-to-one correspondence between characteristic function and a distribution function. So many theorems, many results on distribution function can be shown by using characteristic function. Here we will use this thing. The proof is very simple. So just calculate the characteristic function of Sn by sigma root n. So what is that? Expectation of it Sn by sigma root n, which is equals to phi of t by sigma root over n whole to the power n, because xi's are iid random variables. So if we write Sn as summation xi, then e to the power it summation xi by sigma root n would be equals to product of e to the power it xk by sigma root n. Now since xk's are independent, so expectation of product of variables equals to product of expectation of variables, and so we get this characteristic function of Sn by sigma into root n equals to phi of t by sigma root n whole to the power n. And it is easy to see that if we expand this, the standard expansion, we will get 1 minus sigma square t square by 2 n sigma square plus small o of t square by n whole to the power n. And this goes to e to the power minus t square by 2 as n goes to infinity. This is a standard limit problem. Now it is clear that this e to the power minus t square by 2 is the characteristic function of normal 0 1 or the standard normal variable, and hence by inversion theorem, and rather by continuity theorem of characteristic function, the result follows immediately. So we can say that this Sn by sigma root n follows actually converges to a standard normal distribution as n goes to infinity. So that is the proof of Lindbergh-Levy theorem. Now let us note one important thing, that if we assume that expectation of xk equals to mu for all k, then Lindbergh-Levy theorem basically implies the normalized sum. Normalized sum means we define Sn star as Sn minus n mu by square root of n sigma, that is equals to square root of n into xn bar minus mu by sigma. This converges to tau in distribution. Now what is the meaning of this convergence? That means Sn star converges in distribution to tau, where tau is a standard normal variable. What is the meaning of this? The meaning is, in terms of probability, meaning is that probability modulus of Sn star less than equals to x, this converges to capital phi x minus capital phi of minus x, where capital phi x is the distribution function of a standard normal distribution, that means normal 0 1 variable. So if we just expand this Sn star, we get probability modulus of x bar n minus mu less than equals to x into sigma by root n, and this converges to capital phi x minus capital phi of minus x. So this is the interpretation of the convergence in distribution of the normalized sum of independently and identically distributed random variables to a standard normal variable. So this ensures that, note one important thing is that it has nothing to do with the specific distribution of each xi. So whatever be the distribution, provided the second order moment should exist, then we can apply this theorem. So we can think of any distribution whose second order moment is finite, then the normalized sum of the random variables, say x1, x2, xn, that comes from that particular distribution, they always follow normal distribution irrespective of the original distribution. So that is the beauty of CLT. So it has an immense interpretation and application in statistics. Suppose we are working with a particular estimator and which looks like a normalized sum, then whatever be the distribution, if the second order moment, if we can show that the second order moment exists, then we can immediately say that the normalized sum goes to a normal distribution. So using the asymptotic distribution, that is the standard normal distribution, we can study the properties of that estimator, or we can even use that estimator for testing purpose. So it has an immense application in statistics and naturally in data analysis. Now let us discuss another very important CLT, which is not actually, here we are relaxing the condition of identical distribution. That means here we consider that xn be a sequence of independent variables only, but may not be identically distributed, such that expectation of xk equals to 0 and expectation of xk square equals to sigma k square, which is less than infinity. So then we define small sn as summation sigma k square, that means sum of variance of xk, and assume that summation k equals to 1 to n expectation of mod xk to the power 2 plus delta divided by small sn to the power 2 plus delta. This quantity goes to 0 for any delta lies between 0 and 1 is inclusive. So this, under this condition, so here it is important to note that we are assuming the existence of higher order moment slightly higher than the second order moment, and under this condition it can be shown that capital Sn, there is a sum of random variables summation xk, k equals to 1 to n divided by small sn, this goes to or converges to a standard normal variable in distribution as n goes to infinity. Now we are going to prove this Lyapunov CLT. First remember one thing, that for 0 less than delta less than equals to 1, the condition that summation k equals to 1 to n expectation of mod xk to the power 2 plus delta by Sn to the power 2 plus delta, this goes to 0. This condition is known as Lyapunov's condition. But this is very important in the context of central limit theorems. First note that since we assume that sigma k square less than infinity, then naturally and an expectation of mod xk to the power 2 plus delta less than infinity, we have assumed this thing. And also note that xk is not degenerate for at least 1k, and Sn square goes to infinity as n goes to infinity. Then Lyapunov's inequality, using Lyapunov's inequality, which states that expectation of modulus xk to the power r whole to the power 1 by r is increasing in r. We can immediately write that, and taking, so applying this in Lyapunov's inequality and taking maximum, we can immediately write maximum over k lies between 1 and n, of sigma k by Sn whole to the power 2 plus delta is less than equals to maximum of expectation of mod xk to the power 2 plus delta by Sn to the power 2 plus delta, which we can write less than equals to Sn to the power minus 2 minus delta into summation k equals to 1 to n expectation of mod xk to the power 2 plus delta. Now, in order to prove this CLT, we will use characteristic function again, because we know the usefulness of characteristic function and its relation with the distribution function. And we have two important theorems. One is inversion theorem, another is uniqueness property of characteristic function. So, what is the characteristic function of capital Sn? Let's try to find out the characteristic function of capital Sn by small sn, which is in fact phi t equals to expectation of e to the power I t capital Sn by small sn. Again, just writing capital Sn as summation xk, k equals to 1 to n, and using the property of independence, that means x1, x2, xn are independent random variables. So we know expectation of the product is equals to product of expectation. So using all these things, we can write this phi t equals to capital phi k equals to 1 to n expectation of e to the power I t x k by small sn, which is in fact product k equals to 1 to n phi k t by sn, where phi k t is the characteristic function of xk. Now again, using Taylor's series, we can expand this phi t, we can expand this phi kt and hence phi t later on, to see that phi k t by Sn equals to 1 minus t square by 2 sigma k square by Sn square plus 2 to the power 1 minus delta into 1 plus delta to the power minus 1, 2 plus delta to the power minus 1 theta nk mod t to the power 2 plus delta expectation of mod xk to the power 2 plus delta into Sn to the power minus 2 minus delta. Actually, the last part is not very important in the sense that this would be actually very, very small, so that we can neglect that. This is as n goes to infinity, this would be very, very small. Since we know that log of 1 plus x equals to x plus small o of x, or rather which is equals to x into 1 plus small o of 1 for mod x less than 1, then using the equation 1 and 2, we can immediately get that phi k t by Sn goes to 1 uniformly in k, where k is less than equals to n. So this thing little bit of technical, but here we are actually trying to see what happens to this characteristic function. So if we consider log of phi k t by Sn, this becomes minus t square by 2 sigma k square by Sn square into 1 plus small o of 1 plus 2 theta n k and so on. The last term will again be negligible, as we will see immediately. This is true for large n, and we know that where small o of 1 and theta nk, these two do not depend on k. Hence, summation k equals to 1 to n log of phi k t by Sn. We are taking summation because phi t equals to product of phi k, and taking log on both sides, we can immediately write that log of phi t equals to summation k equals to 1 to n log of phi k t by Sn, which is equals to minus t square by 2 into 1 plus small o of 1 into summation k equals to 1 to n sigma k square by Sn square plus 2 theta nk into mod t to the power 2 plus delta summation k equals to 1 to n expectation of mod x k to the power 2 plus delta into Sn to the power minus 2 minus delta. Basically, although this looks slightly complicated, but if you start writing, this won't be very difficult because we are just using the Taylor series expansion and neglecting all higher order terms in this as n goes to infinity, because Sn square goes to infinity, as we have already seen. So this entire quantity basically goes to minus t square by 2 as n goes to infinity. So log of phi t goes to minus t square by 2, and hence phi t goes to e to the power minus t square by 2. Now what is e to the power minus t square by 2? This is a characteristic function of a standard normal variable. That means when tau follows normal 0 1, its characteristic function is e to the power minus t square by 2. So by continuity theorem of characteristic function, there exists a random variable which is in fact a standard normal distribution whose characteristic function is given by e to the power minus t square by 2, and this is the limiting random variable to which this Sn by small sn converges in distribution, because characteristic function uniquely determines the distribution, and continuity theorem, and by continuity theorem the entire theorem is proved completely. We have already mentioned that if we denote ln delta as summation k equals to 1 to n expectation of mod xk to the power 2 plus delta by Sn to the power 2 plus delta, where delta greater than 0, this is called Lyapunov's function, and ln delta goes to 0 as n goes to infinity, this is called Lyapunov's condition. So this thing is very important, because sometimes in many problems, if we can show that Lyapunov's conditions hold, then immediately under the existence of different higher some moments, or maybe moments up to order 2 plus delta lies between 0 and 1, we can immediately prove the CLT, or we can immediately exploit the CLT under this condition. Now, as a corollary, we can immediately have one corollary which says that if xn is a sequence of independent random variables such that expectation of xk equals to 0 and modulus of xk less than equals to c less than infinity almost surely, that means xk is a bounded random variable, and sigma k square equals to expectation of xk square which is less than infinity. If along with this Sn square equals to summation sigma k square k equals to 1 to n, if this goes to infinity, as n goes to infinity, then capital Sn by small sn goes to a standard normal distribution in distribution. This corollary is actually known as bounded Lyapunov's theorem. Now, let us consider the proof of this bounded Lyapunov's theorem. Clearly it is enough to show that conditions of bounded Lyapunov's theorem imply Lyapunov's conditions. That means the conditions under which this result will hold, that is our claim. This condition, if this condition implies Lyapunov's condition, then immediately we can apply Lyapunov's CLT to get this corollary. Now it is clear that modulus of xk less than equals to c less than infinity almost surely implies that expectation of modulus of xk to the power 2 plus delta less than equals to c to the power delta into expectation of mod xk square, which is equals to c to the power delta into sigma k square. Then if we consider the quantity Sn to the power minus 2 minus delta into summation k equals to 1 to n expectation of mod xk to the power 2 delta, this is less than equals to c to the power delta into Sn square, and this goes to infinity, this goes to 0 as n goes to infinity, because that is our assumption that Sn square goes to infinity. So 1 by Sn square goes to 0 as n goes to infinity. This means that Lyapunov's condition is satisfied. So just by direct application of Lyapunov's CLT, the corollary 1 is proved. Another corollary we can think of immediately, that if xn is a sequence of independent random variables with expectation of modulus of xk to the power 3, that is we are assuming the third order moment which is equals to say nu 3k, and summation k equals to 1 to n nu 3k equals to vn, then if we put delta equals to 1, it is immediately clear that vn to the power 1/3 into Sn to the power minus 1 goes to 0 as n goes to infinity, which immediately implies, that means there is by the Lyapunov's conditions is satisfied, this will immediately imply that Sn by small sn goes to tau, where tau is a standard normal variable in distribution. So the convergence in distribution again holds in this case. Basically this is nothing but a particular case of Lyapunov's CLT. We have proved two central limit theorems, one Lindbergh-Levy theorem, another Lyapunov's CLT or central limit theorem. The main thing that we have noticed in these two theorems are the conditions under which this theorem holds, or the convergence in distribution of a particular function or a particular statistics. We have already considered this one. So in Lindbergh-Levy theorem we have seen that there is an existence of sigma or sigma square, which is the variance of x1, x2, xn if they are IID, So we are assuming the existence of variance, that means moments up to second order. But in Lyapunov's CLT, we have assumed moment little higher than the second order. That means we have assumed that expectation of mod x to the power 2 plus delta. Now delta can be any positive number, it can be 3, it can be 1, 2, etc., maybe some fractional value also. So here we have assumed that the existence of slightly higher order moment than what is actually present in the actual form of the central limit theorem, because the statement of the theorem involves only variance of xi, but the condition under which this CLT will hold requires the existence of slightly higher order moment. So this is a very important feature that we should point out. We should be very careful about this important feature.